In this series of introductory videos on real analysis, we've been revisiting some facts you should have heard in a calculus course. And we've been proving them often with the help of the language and tools of point set topology. For example, recently, the intermediate value theorem. Here we'll prove another very important and familiar result from calculus. This is the fact that every continuous real-valued function defined on a closed interval a,b has a maximum and a minimum value. Recall that a point C in the domain is a maximum point if the function value never exceeds its value at C. The value f of C attained at C is then called the maximum value. If there is a maximum value, it is unique, but it may be attained at more than one point of the domain. The case where the domain is a closed interval a,b is special, since here we can guarantee that every continuous function has a maximum and a minimum value. We will prove this result here using a very special property of the closed interval a,b, known as compactness. For the Bolzano-Weierstrass theorem, we also required a closed interval a,b, and the corresponding property of the interval there was known as sequential compactness. This is the property that every infinite sequence has a convergent subsequence. In this video, we will just talk about compactness, and in our next video, we'll discuss sequential compactness and its relationship with compactness. In both cases, it is not the connectedness of the domain a,b that is important. It has to do with the fact that the interval a,b is closed and bounded. We'll explain these connections over the course of this video and the sequel. Consider a subset A of a topological space X. As explained in our previous video, we can think of A as a topological space in its own right with a subspace topology. An open cover of A is a collection of open sets, UI, whose union contains A as a subset. That is, it covers A. The collection of open sets is, in other words, a set of open sets, or a family of open sets. And it's often convenient to index these open sets in the family using an index set, which we'll denote here by script I. The index set is often a very large set, maybe an uncountable set of reals, in which case the collection of open sets is going to be very large. Now, the union of the open sets in the collection is, of course, an open set in X. I've pictured here an open cover of A. With some redundancy, it is actually possible to throw away some of these open sets and still cover A. For example, watch closely. Here, and here again, and here. And what I'm left with now is still an open cover of A, and it is a subcover of the cover that I started with. Once again, an open cover of A is just any collection of open sets that covers A. We say that a set A is compact if every open cover of A has a finite subcover. This means that given any open cover of A, possibly with infinitely many open sets, I can throw away most of them or some of them, leaving me with just a finite number of open sets from my original collection that still cover A. This is a bit of a mouthful, but once again, an important concept. Stop the video and think about this definition. And in a moment, we'll look at examples. Here are a couple of examples of sets that are not compact. To see that the real line is not compact, consider the set of open intervals of length 1. Clearly, the real line is covered by these open intervals of length 1. And clearly, a finite number of these open intervals can never cover the entire real line, since for n intervals of length 1, their union will have total length at most n, which is finite. So, this cover has no finite subcover. Please note that the real line can be covered by finitely many open intervals, even a single open interval. But the point is that we cannot cover the real line with any finite subcover of the given cover. And to see that the open interval 0, 1 is not compact, consider the open intervals with left endpoint 0 and right endpoint strictly between 0 and 1. These cover the open interval 0, 1, but clearly no finite subset of these will ever cover the entire interval 0, 1. For any finite subset of these intervals, their union will be an open interval of length strictly less than 1. What's an example of something that is compact? Well, it's easy to see that every finite set of points is compact. Given an open cover of this finite set, there's some member of your cover that covers A1, and one that covers A2, etc. Finally, one that covers AN. So you can always find a subcover of size at most n. The main result in this video is the Heine-Borel Theorem. We'll see a more general form of this later in the video, but for now, let's just consider the closed interval 0, 1. And here we show that this is compact. For this, we need to take an arbitrary open cover of the closed interval 0, 1 and show that it has a finite subcover. The endpoints 0 and 1 are covered by some open sets in the cover. Let's say that U0 covers 0 and U1 covers 1. I'm taking some liberties with the subscripts here. Also, it is possible that 0 and 1 are covered by the same open set in our cover. So it is possible that U0 and U1 are the same set, but this really doesn't change our argument at all. Since U0 is open, it covers not only 0, but also an interval extending to the right of 0. I have made this a closed interval from U0 to delta 0, although the definition of U0 being open would only give us an open neighborhood, not including delta 0. In that case, however, you can just replace delta 0 by a slightly smaller positive number, so that I really do get a closed interval. Similarly, there is an open set U1 in our cover that covers the right endpoint 1, and which must therefore also cover an interval from 1 minus delta 1 to 1. Here, delta 0 and delta 1 are just some small positive numbers. Now I just need to cover the stuff in between, the interval from delta 0 to 1 minus delta 1, using finitely many sets from our open cover. I'll be using this language repeatedly, so let's give it a name. We'll say that a subset S of the domain is finitely covered if it has a finite subcover in script U, meaning of course that we can find finitely many sets in script U which cover S. Of course, we need to show that the entire interval 0, 1 is finitely covered. So far, we have a couple of small subintervals on the ends, both of which are finitely covered. They're covered by U0 and U1. If we can finitely cover all the points in between, then we'll be done. Now the question is, how big a subinterval can we find that is finitely covered? Let A be the set of all points little a in the interval, such that the subinterval from 0 to A is finitely covered. Since we've already covered the interval from 0 to delta 0 using a single set in script U, this subinterval is contained in A. Also, A is at most the entire interval 0, 1. In particular, this says that A is a nonempty bounded set. So A has a supremum, which we'll call M. And this number M is somewhere between delta 0 and 1 inclusive. If M is 1, then of course we're done. So, what if M is less than 1? In this case, we need a contradiction. In order for M to be less than 1, it actually has to be less than or equal to 1 minus delta 1. Because once we've finitely covered everything up to 1 minus delta 1, the set U1 covers the rest, and so everything in the interval would be finitely covered. Now, the point M is covered by some set U in script U. The set U is open, so it has to cover an interval of positive radius delta centered at M. Since M is the supremum of A, we can pick a point little a in A, just a little bit less than M, but bigger than M minus delta. So the interval 0a is finitely covered. Also, the interval of width delta around M is finitely covered by a single set U. So the union of these two intervals is the interval from 0 to M plus delta, which is also finitely covered. In particular, the closed interval from 0 to M plus delta over 2 is finitely covered, and that contradicts M being the supremum of A. So, we conclude that M is 1, and we're done. And of course, if the closed interval 0, 1 is compact, then every closed interval AB is also compact by the same argument. But we'll go further by saying more generally, all closed bounded sets are compact. That comes later. First, let's show that closed subsets of compact sets are compact. To see this, let K be a closed subset of a compact set X. So X take away K is open in X, this being the complement of a closed set K. Let script U be any open cover of K. We only need to show that this has a finite subcover. Well, script U together with X take away K is an open cover for all of X. Since X is compact, we have a finite subcover of this cover. Now this finite subcover may or may not include X take away K, but might as well include it just to be safe. Doesn't hurt. If we throw away X minus K, which doesn't cover K at all, what's left must be a finite subcover of K. And that is our proof that K is compact. QED. And now, here is the more general form of the Heine-Borel Theorem. A subset of the reals is compact if and only if it is closed and bounded. In the forward direction, let K be a compact subset of the reals. Since K is covered by the open intervals centered at the origin, a finite number of these intervals must suffice to cover K, meaning that K is covered by the open interval centered at the origin, having radius r given by the maximum of the radii of the finitely many intervals. This says that K is bounded. To show that K is closed, we show that K contains all its limit points. Suppose little a is a limit point of K, but outside K. We need to find a contradiction. Since little a is a limit point of K, there's a sequence of points in K converging to little a. Remember that the point little a itself is outside K. For convenience, we can assume that the distance from an to a is less than 1 over n. If this doesn't hold, then we could replace an by a subsequence that does have this property. The set K is covered by the sets Un as shown. The set Un consists of all points having distance more than 1 over n from A. The only point not covered by these sets Un is the point a, which is, however, not in K. So this is an open cover of K with no finite subcover. If you take only the first n sets from U1 up to Un, they won't cover any of the terms of the sequence beyond the nth term. That's a contradiction. So K is closed, and that proves the forward direction of the theorem. Now we go back and prove the implication in the reverse direction. Here we're assuming K is closed and bounded. Boundedness implies that K is contained in some closed interval AB. And remember, since the interval 0, 1 is compact, the same is true for the closed interval AB. Now K is a closed subset of the compact interval AB. So by our previous result, K is compact. And this completes the proof of the theorem. In the real line, the compact sets are the same thing as the closed bounded sets. This result, by the way, is true for Rn using the standard Euclidean metric. However, it's not true for arbitrary metric spaces. In fact, there are other metrics, even on the real numbers, which give the same topology, but for which this theorem fails. So the Heine-Borel Thoerem should be interpreted as a statement about the standard metric space Rn, or the real line with the standard metric. Let's recall now that a continuous image of a connected set is connected, and a similar thing, as we'll see, works for compactness. We say that a continuous image of a compact set is compact. To prove this, let F be a continuous map from X to Y. In order for Y to be the image of X, we'll need F to be onto. That is, F is surjective. Let's take an open cover of Y. Now we need to show that this has a finite subcover. Well, the preimages of the UIs are open sets, since F is continuous and they cover X. Since X is compact, it is covered by finitely many of these preimages, as shown. Just using basic properties of images and preimages as we highlighted earlier, we find that Y is given by this finite union of open sets, which is a finite subcover of the original cover. Now look at this finite union of the UIs, which is trapped between Y and Y. Since we have the subset relation on both sides, these subset signs must actually become equalities. So we have expressed Y as equal to a finite union of the original UIs. This completes our proof. As a corollary, we can finally justify the theorem from Calc 1 that we mentioned at the beginning of the video. This is an important principle, one of the big reasons, really, for considering compactness in general. The corollary says that if X is a nonempty compact set, then every real-valued function defined on X has a maximum and a minimum. Let's see how this follows from the previous theorem. Let K be the set of values of the function f. Now K is a continuous image of a compact set. So K itself is compact. That means K is closed and bounded. Since K is nonempty, and bounded, it has a supremum. And since K is closed, the supremum M is actually a point of K. So this is the maximum of K. I need to explain a little bit here. If the supremum were not in K, then you would find a sequence of points in K approaching that supremum. So M would be a limit point of K. But then remember that K is closed, so K contains its limit points. The same argument shows that the infimum of K is also in K. So it is the minimum element of K. That's another of the theorems from Calc 1 put to rest.